Okay. Well, thank you everyone for attending the IEEE World Congress and the third of Future Finance Symposium, and welcome. Good morning, good afternoon, maybe good night, depending on your time zone. So today we're going to be talking about digital technologies and sharing the insights of forward-looking technology and business-related industry topics for digital finance. So my name is Elena Yndurain. I am an professor at the IE Business School and a technology strategist. I'm focused in launching new technologies into the market. And I'm going to moderate this talk of two subject matter experts that have been invited to submit papers to the symposium. And they're going to talk about very innovative topics in financial services. So the two subject matter experts that we have are Professor Paul Griffin from the Singapore Management University and Dr. Jorge Sanz from IBM Research. And their talks are going to be focused on high-tech topics in finance. One is going to be about quantum computing for supply chain and trade finance. And the other is going to be about setting up an architecture for artificial intelligence forecasting B2B capacities. These talks correspond to paper 24 and 35, respectively. So I will let the speakers introduce themselves. The order we're going to follow: first, Professor Paul will give his talk. He'll be followed by Dr. Jorge Sanz, and then we'll have a round of Q&A of all the questions that we have from the public, from ourselves, and have a discussion about the emerging technologies and how they're introduced into the market and what is the forecast for each of them. So with this, I will let you talk and share your slides.
Okay, thanks. So let me just share my slides. Hopefully you can see my screen with the title page up. So yes, thanks. My name is Paul Griffin. I'm an associate professor in Singapore Management University, the School of Computing and Information Science. My co-researcher on this is Ritesh Sampat. He's actually a senior underwriter for credit, for supply chain credit insurance, and this is his part of his work from his master's thesis. So let's kick this off. The idea behind this was to explore this new technology of quantum computing, and particularly how can we apply some of the algorithms that have been created now to supply chain finance. So I'll give a bit of a background of the context of trade finance and supply chains, how we approach this particular problem, the data we used, how we process the data. We used 3 different algorithms as well, 1 classical and 2 quantum. So I'll describe those a little bit and the results obtained, and then our final kind of observations and what needs to be done in the future, what could be done in the future. So getting straight into it, the supply chain in finance market size is currently $3 trillion. It's a huge market. If you imagine all of the goods that are manufactured in one country and shipped to another using components from other countries, it's a huge, complicated area with many kind of goods flying around, a lot of financing required for the various parts of that kind of whole end-to-end business process. And it's continuing to increase as well. So from our $3 trillion markets, we have a revenue of 25 billion from last year. We're expecting that to grow up to like 20% over the next few years. This is really due to increased globalization. The world is getting even more globalized, with more countries manufacturing, producing, and shipping goods around. There's more people able to buy around the world as well. Also, the larger companies are getting bigger and more global, and they need to manage their cash around their different subsidiaries around the world. So there's a lot more sort of cash management needed within large companies. And also the smaller companies need better access to finance. So there's a lot more SMEs, the small to medium enterprises, that need to have access to funding. And often they are kind of underbanked, overbanked. They have no kind of credit rating, so they need to be able to access finance. So it's a very sort of large, complex area that we're looking into. Quantum computing is another very interesting topic. You've probably heard about it in the last couple of years. It's a kind of an up and coming technology, a disruptive technology, I think. And I think we hear about quantum supremacy and quantum advantage. Let me just cover some of the quantum advantages. I think the first advantage really is around the potentially enormous processing power which quantum computing can do. I must put the caveat on there as can, because at the moment we are limited to a small number of what we call qubits, and they're noisy and they sort of don't work very well. I mean, they work, but they produce errors in the outputs. But the potential is there, because with a classical computer, you can only really process one value at a time. You take one and you can add 1 to 1, and then you can get 2. And that processing is a kind of a serial process. Of course, you can have multiple processors, but they're still only processing one value at any particular point in time, even though we're now up to kind of gigahertz of processing speeds, or even, I don't know, teraflops or more teraflops. It's still limited, it's still kind of serial. Whereas with a quantum computer, we redefine bits into qubits, quantum bits. And quantum bits are in a probability of being in 2 states. We can still talk in terms of zeros and ones, but they're no longer either 0 or 1. They're actually in a probability of being in 1 or 0. And also the qubits can be in different phases. So we have a lot more kind of informational power to 1 qubit than we do with bits. And as we add them together in a quantum register, the number of values that can be processed at any time when you do a quantum operator on your quantum register of qubits scales of 2 to the power of the number of qubits. So for example, if you have 100 qubits, you can already process a very large number, 1.3 times 10 to the 30 values when you're doing an operation on your quantum register. So that gives you an idea of one of the advantages. Another difference, which I haven't showed here, is entanglement. Entanglement only exists in the quantum regime, not in the classical. So we can actually kind of join together qubits to further give us an extra kind of dimension of programmability to our quantum circuits, which you can't get with classical circuits. So that leads to potential quantum advantage and quantum supremacy. So a couple of years ago, almost a couple of years ago now, Google announced a quantum supremacy, where they had a quantum computer which could process or solve a problem in 200 seconds, which would take the sort of biggest classical computer 10,000 years. So that's why they called it supremacy, because you can't wait around 10,000 years. You can wait for a couple of minutes. So that's a sort of claim for quantum supremacy. Fortunately, the problem they were solving wasn't exactly one which anybody wants to solve, but still, you know, the point was made. And IBM did come back and say, well, actually, we could tune one of our supercomputers, and we could actually do this in 3 days rather than 10,000 years, which then I think brings up the question of, well, okay, it's a quantum advantage rather than a quantum supremacy. So we're looking at either of those would be fine. I mean, quantum supremacy would be great, but quantum advantage would also help many businesses. 3 days or 3 minutes instead of 3 days is still a good move forward. But they're not going to be replacing classical computers at any time, not even anytime soon, because we live in a classical world, so we need to input classical numbers and get output of classical numbers. And also quantum computers are better suited for probabilistic calculations. 1 + 1 on a quantum computer doesn't necessarily give you 2. It'll maybe give you 2, maybe give you a bit less, bit more. It's a probabilistic, non-deterministic system. So if you want to develop an accounting system where 1 + 1 = 2, then I suggest a classical system. If you want to do more probabilistic type of calculations, then quantum computers may be a good solution. very nicely. Actually, over the last few years, there's been many software frameworks and languages to program quantum computers. They're readily available and pretty free to use as well. IBM has their Q system. There's Penny Lane for quantum machine learning. There's many others available as well. So it's definitely a good time to get started. And yeah, develop your quantum applications and test them out, at least at the scales we can now. So coming back to finance, there's many areas which are being explored where quantum computers can be, or could be useful. These are, say, sort of the non-deterministic type of problems: credit scoring, portfolio analysis, forecasting markets, looking for arbitrage opportunities, pricing derivatives, and various types of risk analysis. They're all possibilities where quantum computing can be an advantage. There's a good paper to look at from Roman Orris and co-authors for a general overview of quantum computing for finance. So I'd recommend to have a look at that if you're interested. So with those two pieces of the puzzle in place, what we wanted to do was really explore how good or how easy it is to use quantum computing. Sorry, went back a slide. How easy it is to use quantum computing to try and optimize a supply chain finance portfolio. So you're probably familiar with stock portfolios where you have a number of different types of investments. You want to maximize your returns from your investments, and you want to minimize the risk of not getting those returns or making a loss. Similarly, in trade finance, there are many types of financing. Maybe the exporter needs money to be able to manufacture, or the importer needs to be financed to be able to receive the goods and pay when they arrive and before they can get their money from their customers. So there's many places where financing is needed, but it's not in terms of looking at the stock prices. It's more different kind of risk metrics, which I'll go into a bit later. So we wanted to set up the problem in that business context, evaluate some quantum computing algorithms that are already created in IBM Qiskit. They have some tutorials and algorithms available, and then compare the accuracy of the algorithms kind of to themselves, but also to kind of a baseline. So we took the baseline of manual underwriters. We have a portfolio which manual underwriters would decide, given the risk profiles, which would be the best selection, and use that as a baseline. So how does the computer compare to a human? So what we did is select a number of companies. I'll show those in a minute. Obtain publicly available data for those companies, such as kind of annual reports, quarterly filings, sector risk reports, a whole bunch of data, but it is readily available. Then we took 20 key parameters which underwriters use in order to assess the risk profile of the companies, weighted those, scored them up, and then took that data and put it into our algorithms to see what they come up with, to try and optimize this portfolio of finance. So we took the data, selected the companies, looked at the factors. These are the companies. We took 10 companies across 2 sectors. Actually, we took more than that, but for this particular presentation, we're looking at 10 companies across 2 sectors and across different geographies. So you'll probably notice some names. One sector was department stores, and another sector was steel. Obviously, there's a lot more diversity which could be given to a portfolio in the future, and you'd probably want a lot more companies as well. But this was the size we can use to kind of prove the concept. So yeah, department stores, Woolworths, Tesco. In the steel, we had Nippon Steel, ArcelorMittal. So relatively big companies. We can easily get the data and assess the risks. So the key problem here really is always sort of mapping your business problem onto your quantum algorithm. So the algorithm, this is a sort of optimization algorithm with constraints. So this is our basic okay, sorry, they were optimizing algorithm, looking at trying to maximize the returns and minimize the risk. So with a stock portfolio, this is a relatively common practice to take the price changes in your data set, look at the standard deviation, which gives you sort of the volatility. We say that the volatility is a sign of the risk. And so the risk comes from the price change standard deviation. And then the returns is how much, again, on the prices, how much has the price moved up or down? If the price goes up, then you can probably sell it at a higher price and make money. If the price has gone down, if you sold, then you would lose money. So the risk and returns come from the price movements. With this particular problem, we don't have that. We don't have that sort of time series of prices. But the risks are more looking at the particular parameters for a company. So we have 4 companies in this particular part here, showing Olam, Whitehaven, JSW, Tesco. And we have, we took 20 different parameters altogether. We're just showing the top 12 here. So the company's liquidity, how much cash do they have available? How much money do they get from their day-to-day operations, debt equity levels. So we have a score for all of those parameters. Those parameters are different, have sort of different weightings compared to how much risk they give to the whole company. So this is a manual task to kind of rate or weight these different parameters into an overall kind of risk score for each parameter, and then rolled up for each company. But once you've decided, maybe they'd be different for each sector, but they wouldn't be different for the each company. So that's pretty static. This is the equation just kind of showing this. This was done in Excel outside of the quantum computer to prepare the data first of all. Then for the return aspect of things, then we looked at the interest rates we would get from the loan. So some companies or some industries would have a higher interest rate, basically because they're either loaning more amount, or the risk is more, or their credit rating, for example, whereas other companies would accept. This is also very much a negotiable point between the company and the lender as well. So whatever interest rate you've ended up with would be your return for that particular company. Okay, and then we calculate the covariance of these risk metrics for the algorithm input. So the algorithms themselves, we took, say, 3 different algorithms. One is a purely classical algorithm, which is called the sort of eigensolver, tries to find the minimum. If you imagine that your optimum profile is like a landscape, and you're trying to find the minimum point in that landscape, this will try and find what they call the eigenvalue for the minimum of all the different types of combinations you could use, what has the optimum in terms of the lowest risk or highest return. Then we also had a variational quantum eigensolver, VQE. So this is doing the same sort of job, but now using a quantum circuit, and it's trying to optimize the quantum circuit to give you the optimum solution. It's kind of a machine learning where it's trying out different qubits and operations on those qubits to try and find an optimum circuit to give you the best solution. And another version of that is a QAOA, quantum approximate optimization algorithm, which is similar to VQE in that it's varying this quantum circuit, but also uses further operations to optimize on classical computers as well. So with those 3, this is the problem we're actually trying to solve. So we're trying to minimize this function here, where X is the flag whether a company is picked or not. There's no kind of in between. You either choose a company in your portfolio or you don't. So this is essentially an array, a kind of a one-dimensional array, a vector of whether a company is picked, which we give a 1 value, or it's not picked, in which case it has a 0. Then the mu here is the returns, in this case, interest rates from the different loans. We have the sigma is the covariance across that matrix, and then Q is our risk appetite. So we'll be varying the risk from having zero risk, which means we don't want to take on any risk at all, or we don't care about any risk at all, in which case we're only concerned about the returns up until having being risk adverse. So with a high Q value, the investor is being risk averse and it's more concerned about minimizing risk than it is about maximizing returns. Couple of constraints. So one is the algorithms are supposed to use up all the budget. So if we have 10 million, which we are able to use for financing, say for loans, then we want to use the whole of the budget. And the other constraint is that all the financing amounts are the same. So you can see here already there's room for improvement on a real life situation, but these are the constraints to keep things simple at this early stage. So yes, we take these terms and map it onto this landscape, this Hamiltonian function, and then run the algorithms. Because the algorithms are kind of essentially doing the same thing in concept of finding this this minimum, then the programming interface is actually pretty much the same. So we can just slot the same data into these algorithms and run them quite efficiently. So from the programming side, it's quite straightforward. So onto the results. We can see here that we've got 10 companies altogether. We have, these are the acronyms for the companies. Then there was, say, 10 companies. For this example, we select 6 companies. So we have to choose 6 of these out of this 10. These are marked with 1s and in green. So this is what our manual underwriters decided for these different risk levels, which ones they would choose. Then we ran the same sort of selection needs through the classical algorithm. We can see the results here. Then the VQE and then the QAOA. So there's a few kind of observations here, first of all, which I think are interesting. We haven't gone into any of the details as to why these observations occur, and that could be very interesting conversations with people who wrote the underlying algorithms. But first of all, the classical is very stable, not necessarily right all the time, but stable. VQE is quite stable as well, and it comes up with 6 selections, but QAOA has the most kind of variation as we're increasing the risk. As we see from the manual selections, we don't necessarily keep swapping our choices just because the risk has gone up a little bit, but QAOA is moving around quite a lot. Oh, sorry, my video has gone off. Also, the other observation from QAOA is it doesn't always meet the constraints, which is a kind of a concern when you're trying to optimize portfolio for relying on having 6 assets. Then sometimes you get 3, sometimes we have 7. So something is kind of going on there. Could be the way we're using the algorithm or something else going on. But we have seen that with other uses of QAOA in other projects as well. So that needs kind of further investigation. So with these selections, we then come up with an accuracy score. So we say we assume that the humans are correct, and our manual is the sort of truth of what is best to select. Whether that's right or not is a matter of opinion, but we're going to choose that as our baseline. And then now we look at the corresponding selections for the 3 different algorithms. So now a 1 means that this algorithm selected the same asset at the same risk rate as the manual, and 0s means they didn't. Then going across for each of the 10 for the risk ratings, we count up how many hits we get for each of the algorithms and then sum up to give us our overall accuracy score. So looking at these results, and also looking at a number of different selections as well. So this was the 6 which we were looking at previously. We also took 5 selections, 4, 3, 2, 1 to give us some more data. I think we can see generally that all the algorithms are getting more accurate as we have more selections. So that means that it'd be worth pushing these algorithms and data to bigger data sets and see what happens elsewhere. You can say the classical looks like it's the winner at the moment, although we did some statistics on the data, and it's not really statistically convincing that the classical is necessarily the best. And in fact, the VQE may be still, we are, I think, within tolerance, but the VQE seems to be doing a better job as we get more selections. But this is all conjecture, not statistically proven. QAOA does have more variance in the results, as we can see here in this table. And the simple ANOVA shows that we can't really state that there's a big difference, because we have a p-value of 0.4, which would imply that you can't really say that any particular group is better than the other. So in terms of conclusions from this, I think we can safely say that quantum algorithms were similar to the classical. I wouldn't rush out to necessarily swap over right now, but they are similar in the behavior, and they perform to optimize a portfolio against the manual in a similar way. Potentially, we could see that they could outperform if we have larger data sets, if we have more selections, which is much more realistic. We of course make it more sophisticated in terms of having varying amounts as well. So there's a lot of possibilities there. And as data sets grow, we have more parameters as well. As we get data from IoT and social media, then that could actually help to improve. I think it was very nice to see that we could relatively easily use the hardware and software to explore this particular business case. It did take some thinking to map the business problem onto what the algorithms were kind of looking for, but we could then kind of relatively easily program. So the Qiskit programming environment is just Python code running in Jupyter notebooks. The IBM backends have two different types of simulators, and then a number of hardware backends as well. They're all exposed through an API, so the programming, if you know Python, is straightforward. And then really, yes, around the sort of manipulating the data to be ingested by these quantum algorithms. And then at least for these smaller sizes, you can compare and test the applications against sort of classical quantum and what you might expect as an expert user. So in conclusion, or looking to the future, I think we are seeing an increase in the number of transactions. So we're seeing a lot more smaller transactions within the trade finance space. So that industry is growing, not just in terms of the number of companies and everything involved, but also the number of transactions as well. As I mentioned, there's an increased availability of larger data sets to be able to help this assessment of risk. So we can have information coming from IoT devices as part of supply chain logistics. We could look at social media for how people are seeing companies and products, etc. So all that could be fed in if we have the sizes to be able to do that. So I think in the future, we will definitely need to apply quantum computing to be able to deal with the speed and the sizes of the data to improve supply chain financing. But for that, we do need to see a further improvement of quantum hardware, which is coming along. I mean, almost every week there's some new step forward in quantum hardware, whether it's photonic devices or superconducting devices or ion devices. The main vendors are improving their hardware all the time. Connectivity with quantum networks is also improving as well. So it's very hard to put a timeline on when this would be production usable. let alone production ready. But yeah, I don't think it's going to be that many years away before we can see some real use cases. And I think this shows that when the hardware is available, the software is already there. So I think we should be able to see a lot of business cases being able to be applied to quantum computing. So that's pretty much the end of this presentation. I hope you enjoyed it and open for questions.
Okay, thank you. Thank you very much, Paul. So we've heard, sorry.
I say John Howe has his hand up. I don't know if he wants to say.
Sorry about that. Yes.
Okay.
Jen Hao, do you want to say something?
Oh, I didn't raise my hand, just Paul.
Okay.
Oh.
Yeah, just clapped my hand.
Oh, okay. All right. So we heard about Paul. So Paul is a member of the faculty of the Singapore Management University. He teaches IT and fintech, but he also has experience in corporate experience advising companies on how to use IT and about technology strategy. And now we're going to switch to Jorge. So Jorge works at IBM Research, and he's a chief innovation officer for banking, working in enterprise artificial intelligence and systems and solutions. But he also has an academic background because he has worked in computing and business schools as well. But I'll let him introduce further himself and talk about the fascinating world of artificial intelligence. Jorge, the floor is yours.
Awesome. So first thing first, let me thank you, Elena, for the invitation to be with the colleagues in IEEE today. And almost equally important, let me say that I thank you very much for being up and helping the success of our financial services technologies and future symposium by because you are in European time zones, and my understanding based on the last 4 sessions we have is that you've been up since 3 a.m. in the morning or even earlier. So I want to thank you very much for your support in organizing all these and for being with us steadily for the last several hours in such a difficult time zone. Okay, so it's almost 10 p.m. in California now. So I'm following your path. And what I'll be doing is I'll share my screen briefly here, and let me pick the charts, right, and do so. Let me change the subject and show the actual charts. Just bear with me 1 second, please, okay? I have some problems with the projection, okay? So let me share.
No problem.
Can you see anything on the screen?
Not yet.
No, right. You cannot see anything, right?
Not yet.
You can see that Jorge has started sharing screen.
Yes, what I'll do is I will stop sharing and share again. Okay. Can you see the screen now? Probably not, right?
No, unfortunately, just the video at the moment.
Okay, let me try once again. Just bear with me. Let's go once again. And yeah, I'm trying to find the screen here. usually I do this daily with no problems, but you know, the common Murphy's law, right? So let me just share it once again and see whether we are luckier now. Let me close it again. Open it up again. And let me know if you see it, okay?
Start, yeah.
Yes.
Right.
Now you can, okay? Good. So I hope I can switch the slides. Let me see if I can switch off my video. I think there is a bandwidth problem overall that is not letting this. Let me stop the video and see whether that helps. So can you see the screen more clearly now?
We can see it well, yeah.
Okay, good. So what I intend to cover today, you know, passing the slides is extremely slow, right? So and I don't have many applications, but now you can see that, right? You can see. So the outline that what I was hoping to do is share with you some practical considerations for AI in finance. And those are motivations for some of the challenges that we find in practice with AI, and then regard the architecture and service practices as route to scalability, which is part of the promise of the work that I'm reporting here, and then have some conclusion, next steps, right? So let me go directly into what I've been doing for this domain in practice, right? So I've been working on engagements in AI, analytics, and digital transformation for a number of years, probably over 15 years by now. And these are some of the engagements that I've been working on in the last 10 years, covering a variety of industries and line of business and different type of industry segments, even more inside finance, for example, working with financial markets, companies, banks around the world, and many CFOs. And I'm clarifying that because chief financial officers do finance. It's not just financial services. And this is a very important aspect of the financial domain that you will see reflected in some of the B2B areas, right? So all the work that I'm reporting is coming from actual work and engagements with companies, and most of them are on the screen at the moment, right? But there were others in the last few months that I've been working with. So of course, not all those companies have to do with finance. Even some of them, the CFOs have been involved in doing some work that have to do with different capabilities. But when you intersect these companies with finance per se, right, I want to focus on B2B scenarios that scope AI in finance. And there are a number of reasons why I'm doing that, right? But before I get into why I'm selecting these scenarios, which I believe is very important, these capabilities that are on the screen at the moment reflect different things that happen in finance in different segments of financial services. Like, for example, I mentioned the CFO as being a cross-industry line of business where people do finance, right? So you have accounts receivable forecasting, for example, which is a foundational problem for CFOs. Balance sheet forecasting, that is a very important problem. Material pricing, which is another very big problem. Account payables, and receivables, both the analytics role that it has in estimating cost and revenue projections, right? These are part of what people use in what we call planning and analysis in finance, right? And these are ranging from corporate finance to regional finance that is done in, on the field in many pricing subjects and projection of revenues, et cetera, et cetera. The second area is counterparty risk. That's more typical of financial services organization. It could be both banks and financial markets, people that, I say both because, for example, collateral loan obligations or collateral debt obligations, right, that have been, today, they are still an important instrument. They are created by financial market people, and banks and others buy these elements. So, but the counterparty risk alludes to, in general, assessing risk of lending money, essentially, right? And that's what it is. And assessing risk in the sense of how likely is that the company being assessed, SME, small, medium enterprise, or it could be a large enterprise, how risky they become in terms of the ability to repay debt. That essentially what the risk is all about, right? So that there are many types of risk, but this counterparty risk is specific on distress, default, corporate bankruptcy probabilities, et cetera, right? So debt forecasting and so forth. So then there is another area that, I won't have the time to cover all of these, but, for people who work in computer science or information technology, all these things will look alike. And for people who work in finance, they're all different. So this is one of the challenges that I have found in terms of engineering practices and computer science practices, that in creating capabilities for the finance domain, particularly in AI, I will use AI and machine learning completely interchangeably, right? But it's not the same, but I will use it as if they were the same for simplicity. Part of the things that we see in engineering and computer science work is that people forget what are the phenomena being modeled or studied. And the phenomena studied or the phenomena being modeled alludes to the behavior of people, organizations, markets, right, in different level of granularity that explains the provenance of the data that is being used for the model. So in two process generation and practices that are very distinct, very different, the techniques that we use cannot be ignoring the provenance of the data for any modeling work. And the reason I'm highlighting these B2B scenarios and as exemplars of the importance of understanding the competence in order to do good engineering, good computer science work, which is, after all, designing innovation for technology capabilities that help these people do their jobs better, right? That's what it's all about. And so the reason I promised to say a sentence about why B2B, I came to the conclusion that given the status of regulatory issues, particularly in Europe and in other areas of the world as well, the use of personal data for anything that has to do with analytics is a subject of enormous risk. And banks are probably among the industries that I know the most sensitive in terms of governance, risk, and compliance practices on what they do with personal data. Now, in these domains that are on the screen, there is no personal data. And even for financial crimes, and even in the markets that there are most sensitivities and tensions, comparing crime analysis with civil rights, which is personal data, even in those markets like Europe, which is extremely sensitive, the boundary is very clear, because a due diligence for KYC in case of consumers even, which could be ultimate beneficiary ownership determination and so forth, that kind of analysis is okay, because it's done for crime compliance practices that use personal data in certain due diligence ways that is pre-established, very clear in rule and regulation that bank or other financial services follow, right? So for the rest, there is no personal data investment here at all. There is nothing in the data collection processes that would be under the jurisdiction of GDPR, for example, or PDPA in Singapore, or the California Consumer Protection Act, and so forth, right? Because all this data is pertaining enterprises, and none of the concerns of personal data applies for enterprises, okay? So that's why I'm focusing on these things, because I believe they are cleaner, even though I must say that there is a law in Europe upcoming, which is an AI law, that catalogs risk in AI in very, I would say, very, very wide ways, and it's a very important piece of law that is it's not enacted yet, but it's at the latest stage in the European Commission and the Parliament consideration after the consultation with all the member states in the European Union for being sanctioned. So there is a high likelihood that this is going to happen in the next few months, and that regulates AI irrespective of whether it's consumer markets or it's enterprises or whatever it is. It's about regulating AI for AI risk areas, and so that's one disclaimer that I want to make. And the second one is that even in decision making on small, medium enterprises and corporates, anytime you use a black box in AI or machine learning, you will be confronted with some issues of so-called explainability. And this is not necessarily a matter of law. In the concert of consumers, it's definitely a matter of law. In GDPR, for example, you cannot make decisions that are automated without having a rationale by which or whereby a consumer may ask you on what are the foundations for the decision. And this foundation cannot be explained by saying, oh, you know, I apply the 3-layer neural network in which the 2 parameters that are in the middle are alpha, beta, you know, one is the square root of the other. And it happens that when that happens, you will not receive your loan, right? So that is not going to be anything that we would call compliant and in the European Union. So I want to clarify that even if GDPR applies to consumers, and that is specifically the situation for a consumer, right? Because that law is for personal data. For enterprises, governance, risk, and compliance officers in a bank will never like to have, at least I did not find yet any compliant officer in any bank on the world that will say, oh, it's okay to have a black box whereby I will determine whether this small, medium enterprise will receive or will not receive a loan. It's not gonna fly as a best practice because of the risk entailed for other resources that enterprises have for practices that may be brought to court for reasons that go beyond personal data, okay? So now I think this is the most important chart of this discussion, right? And I want to divide the experience with AI in two different segments, right? One is AI viable? In other words, do we know whether it solves problems? That's the viability that I'm talking about. There could be productivity issues. I mean, does it take me too long to determine the viability of something that I'm doing with AI? Those are the first bullets under the viability and productivity issues. The second set of bullets is about, okay, assuming that I'm getting something useful in certain circumstances, can I claim that I have a scalability of that outcome? And there are many ways of reading scalability. So frankly, I believe this is the main chart of the story, right? Because that's where I'm collectively putting together years of delivering applications and in many cases struggling with some applications, and collectively using the experiences and the in some cases anecdotes to professionally said from other people who work in conjunction with me and with colleagues very close in service practices that we have, right? So let me go first into the couple of bullets under viability and productivity. Let me give you some instances of what people find in reality, right? Many works in modeling for machine learning needs a case-by-case approach. And that means that for every problem, you feel like you are starting from scratch. So you get new data, and now you go and begin trying to discover what to do with that, what model is the appropriate one, and you go through a number of trial and errors. It's like the tools being software driven, obviously, algorithmic stuff. You go and begin customizing, tuning, and you go through a process that process is what people call, probably for a lack of a better term, data science. It's a process of creating models from data. And that process is extremely time consuming, not only because, and I will mention other things like, for example, reason for the data to support machine learning is not ready. It's not clean. It has missing values, parameters that are not necessarily measured. It's not just being dirty or not dirty. It's that data provenance maybe was never created with the idea of observing a system with the consistent that is needed to build models who will work by recording all the information that was needed, particularly in processes where there is a lot of human intervention in banks. It's very hard to record every piece of information that is relevant to what people are doing in the process that determines the input variable of a model, right? It's not always observable. There are a number of reasons for that. So then you have computational issues. You try some idea that is very lengthy, very time consuming. It has a huge pool of data, very big data sets, a lot of computing. And then with the internal resources that you have and the internal systems that the organization may have, you may not necessarily have all the computing power to do that in minutes or in hours. So it may take days or weeks. And part of the reason why people don't necessarily benefit from the scalability of solutions that come on cloud and things like that, which is the next item, is because data cannot leave the firewall. So, and this is not about personal data. Some people think that banks don't move data around because it's personal data. It has nothing to do with that. I mean, well, let me take that back. It's even more serious for personal data because of the implications of the law. But even for data that is, for example, financial data that come from analysis that is being done internally in risk management practices in the bank is seldom going to take that out from the core systems that they have internally. So they may still use cloud, but it's going to be an internal cloud It's not going to be a public cloud. They're not going to be migrating data sources in quantities in and out of a public cloud for benefiting from the scale of algorithms that are available on some of the public cloud providers that we have for machine learning and so forth, right? So finally, there is another factor that is in the viability and productivity, which is the gap between decision makers and people who do AI. There is a huge communication gap. There is a huge understanding gap between culture, I would say business background versus non-business background. And that comes to be an issue when it's going beyond the sandbox of doing machine learning in a certain center of competence or center of excellence in an organization. Is when you want to take that out of the sandbox is when GRC people in an organization will come to look carefully into what you have been doing, and in convincing them that there is a robust story out of the models and the things that need to be taken out of the sandbox, there will be a lot of tension in many cases. And the tension comes because of this duality of background, duality of understanding, duality of objectives that may be resolved. Part of the architecture and the service practice work that I've been doing with other colleagues in IBM, in IBM Research, is precisely to try to address, in particular, that issue, right? So, so the scalability now. Actually, to be brief, I can actually go, let me go to the next chart that I believe it gives a visual view rather than the bullet. But if I miss any bullet, I will go back, right? Because here, you know, people talk about scalability, but I tell you, and I'm saying this in a very humble way, they talk about scalability, but they don't know what they mean by that. So, for example, let me go back, right, 1 second and tell you a business interpretation. When you talk to a CEO in a bank, when you say scalability, it will be the last bullet, right? The CEO getting impatient due to limited balance sheet impact. The CEO doesn't confront, you know, the CEO is not going to be happy because you resolve a problem here, a problem there, or you have some visibility with your favorite, you know, funding agency or international organization that you're showing off. I mean, it's okay for branding purposes, right? But this, you know, after investing for a few years with a lot of headcounts and resources, people are going to be impatient, right? So that is one aspect that when you talk to a top CTO or CXO in an organization and they talk about a scalability problem, is to say, listen, how do I make money that is visible on the balance sheet? That's what it means. It's not, oh, you know, I have an issue in taking too long to resolve a problem. There may be many productivity issues embedded into the problems or challenges, but the manifestation is that level of aggregation. Okay, now, when you look at this, it's a bit more technical, going into what scalability really means, right? And this reflects different examples and experiences that I had myself, and in some cases with others as well. It's not just me, right? So let me go one by one, right? One of the clear issues is that as the problem of dealing with the data engineering work, it becomes so prominent, it's so time consuming that it's one of these issues of productivity that becomes an impediment to repeat the experience faster from problem to problem, right? So that's the simplest one. That is the consequence of aggregated productivity issues, that you change data set, you bring another line of business with another problem, and you start from scratch. And then there is a huge complaint in many data science people and people in center of competence saying, look, we take a lot of time in doing data engineering as opposed to what we are better for the data science people, right? Which is modeling with data, finding models and so forth. So that's one. There are more subtle ways, right? Like, for example, it takes very long to go from, people in data science talk about data insights. I never found an organization that pays for insights. So, it's a nice word to use as a buzzword, but the reality is that organization pays for operational impact. And what I mean by that, and it's the arrow in the lower part, right? Moving from data insight to a full operationalization means make the AI-driven insight into a process that the organization uses that is going to be deployed in the field at the scale needed to become relevant. For example, I have an idea in a corner for doing great machine learning with some data that come from ATM systems, right? ATM, I'm talking to, about the system, right? The ATMs in a bank. And I can model for a couple of data sets that I got from a couple of ATMs, a great idea for detecting when the ATM is likely to fail within the next, it's a problem similar to asset pricing in some ways, right? Because of the time probability model, right? But this is about sensor data, has nothing to do with assets, but it's okay. So I model the probability of failure in a certain given period of time, right? So how likely, and then I can do some preventive maintenance by dealing with the scheduling ahead of the fixed asset planning maintenance or asset maintenance planning that I may have. So, okay, that works for 2 ATMs. Now, when you want to make this scalable, means that you need to take that insight that you got from a model and make it into the ATM for the entire bank. And this may have 7,000 ATMs, right? I've seen this also outside of banking in other manufacturing areas as well, where you have a lot of different models or variations in the systems moving from one ATM to another. And when you want to deploy the capability that you had in AI for the model that you are embedding into that process, which is getting sensor data and doing the analysis, not necessarily in real time, you can do it offline, every day or so. Unfortunately, it's going to take so much tuning, so much changes in what your original insight was, that it may frustrate the operationalization. That's another example. Another one, many of the arrow toward the right, the green arrow, right? Elena, you have a question?
No, just let you know you have 5 minutes.
Fantastic.
Yeah,
thank you. The evolving, there is many of the algorithms that people use are findings that have been created or tried so we have a huge pool of open source. It's a phenomenal source of, I would say, intellectual capital, right? It's the biggest force in the world for contributing to AI is fundamentally coming from open source, okay? And it's being fueled more and more. Now, however, that makes the universe of your pool even bigger, but you have no guidance on what is going to be better for the problem that you have at hand. And when you take a finance problem, right, and you face finance agnostic pools of capabilities, the gap is significant. It takes a lot of time to even have guidance on what you can use that will make sense for the type of data provenance and process that you're trying to affect by using any machine learning. Finally, going from one process instance or one process in an LOU, so in a LOB, business unit, made all the way into other processes, right? The process variation when you go from, even in the same LOB, when you go from one geography to another, or one region to another, or one branch to another, there may be variations in data that reflect different policies that have been used that will surprise you if you don't act early enough, and it will impede the scalability of your nicely working good idea. So how we approach the solutioning for these things is essentially, and I will close it here because you can read the details on the paper. We envision some guidance that is essentially a composition of 3 dimensions, right? What are the design elements that matter for creating AI algorithms that work? What are the building blocks, modeling capabilities that are suitable to certain competencies in finance and not for manufacturing or other areas? That's the second dimension. And the third dimension is, you remember all the issues in productivity and scalability that I mentioned. Some of them, as I said a bit, there are gaps in the organizational practice. This is work that doesn't stay in a corner in a center of competence. It takes an organizational cooperation and cohesive practice that allows particularly large organizations make that practice, or consulting or in system integrations organizations that help companies achieve that service, become governance practices that are part of what the enterprise does for a living in terms of knowledge and management inside the enterprise, right? So this is what you will find in the paper. There are a couple of pictures in the paper that are these are design dimension examples of what rationale you have to follow as a first pass through filtering and understanding building blocks that are the modeling capabilities that apply to some B2B areas, as I've been mentioning. So, for example, if you want to explain your results, what capabilities you have that are going to give you reasonable insight for what you want to say in explainability when you have a certain type of finance problem in some of these line of business. That's what I mean by filtering from existing capabilities into reusable, sensitive, logical building blocks that have a hope to achieve what you are intending to do. And finally, the service practice, or the work practice, if you like. Maybe service practice should be better for naming the entire approach, right? But the work practice is, okay, end to end, I'm given a problem. What are the elements that I have to take into consideration? Activities is really like, I mean, it's a work practice. It's what do I need to do cohesively in the organization, end to end, to ensure that I can scale in spite of the productivity issues that I may find, right? In some cases, there would be blockades. In other cases, there would be the result of the organization working too erratically, right? And that doesn't help when you want to have a large group of people that involve business decision makers, like the CDO, the chief data officer, people in the line of business that have the responsibility for P&L, right, for the profits and losses, et cetera, et cetera. So this is a combination that affects different role players, starting with GRC and the legal assessments that should be done very early, not at the end, not after you have the insight, you call the lawyer, right? So that's not the way to work. And many people, that's the way they proceed, and they find the hurdles when it's too late, right? So people stop you when you don't have any other chance to move forward, but that's too late from a service cohesive practice in an enterprise, right? So the rest is in the paper, Elena. So I think it's a good point to stop here and let you formulate the question for the interesting talk that Paul gave. and let you go to sleep, by the way.
Thank you. So thank you very much. Actually, the questions that I have are they're for both of you, right? So you were both talking about two disruptive technologies, so two technologies that are completely changing how business is done, but they're at the different stage of evolution, right? So AI is more advanced. Obviously, companies are already using it, but yet, Jorge, you were mentioning how there's still a lot of work to be done to scale it. There's still a lot of work to be done for regulation, right? So to really make it a mainstream in a way. And then Paul was talking about quantum, and he is at a, well, his technology that he was talking is at a earlier stage, more of a proof of technology, proof of concept, right? Testing, how well does it work? Now, the question that I have for both of you, if we think from a people and operations and technology, so if I'm in a company and I want to, and I haven't yet deployed either AI or I haven't tested quantum, what do I need to think about? Like how, in terms of what I have in my organization, will the skills that I have be reusable for AI and quantum? How well can I integrate these technologies with my current systems, right? So how well does quantum work with my systems? How well does AI, right? Or is it like something that's in a silo? And then finally, how will it scale? How is this technology going to scale? And in relation with corporation, with enterprise systems. So I don't know who of you wants to start answering, but it's the same question, but for different stages of technology.
I mean, I can jump in if you like. I mean, so I worked in banks for 15 years in the IT side, developing and pushing out various systems, particularly on the trading and market side. And this whole question of technology evolution, legacy systems, disruptive systems, new systems is across the. It's always been there probably since the mainframe days. And it's just kind of I think it's getting bigger and faster as we go forward. And I think the question of skill set is very important. We probably should throw blockchain in the mixer there as well, which is kind of in between that maturity stage. You've got AI, which has been around for some time, still being embedded. Blockchain is starting to get used in a number of companies, and it's starting to show that what it can do. And then quantum computing is on the still on the well. We haven't actually got a practical advantage yet, but it's an interesting technology. And I think it's some sense it's a moving goalpost that. From what I've seen and the people I've kind of employed in my teams, I want a kind of a set of people, and as sort of working as a project manager as well, I want a set of people, some people who know the business really well and really don't care about technology, some technologists who know the technology really well and less care about the business side, and then the people in between who sit between those two. And the more that technology understands business and the more business people understand technology, the better. But you've got to have the experts in the fields, and they need to have a kind of a language. So I think Jorge touched on this, is that it's they've got to have a language and try and bridge that gap somehow. And I think we also need tools to be able to do that. I think that's also where consultancies and vendors can come in to kind of bridge that gap. So you don't want to, I think, entirely rely on vendors, otherwise you can get kind of locked in, and that can be a risk as well. So it's, but then also if the vendors are the deep technologists, particularly for these areas which are now getting very complicated, the crypto stuff in blockchain, the quantum stuff in quantum computers, that's not a sort of thing that an average techie in a IT team is going to know or necessarily spend the time on. So for me, it's a kind of you need a diverse team with the people can cover the different areas and then be able to bring those together in a common language, whether that's using diagrams or documents or just getting people together to understand the different aspects of the different people involved. Not easy, yeah.
Definitely not easy. And how about for a more like moving forward in a technology that's more advanced, like AI? How do you see it, Jorge, in comparison with quantum?
In comparison with other
with a technology that's less evolved, right?
Yeah. So I'm thinking, because I don't want to misrepresent any market leader, right? In the way some banks and some financial markets people do some things, like for example, in hedge funds, people really take analytics, machine learning, and all these things, right? Extremely seriously, because they get a significant advantage from forecasting and things that they do for a living, for their own product definition, for their own investment portfolios, right? So the answer in terms of, I would say, adoption of technology may need in finance to divide a bit the financial services segments, right? Because they are not all equal, right? So people that have a huge appetite for computing portfolios with some of the optimization techniques that you, Elena, had been working on in quantum, right? In your own work, in your own teaching that you do, and the work that Paul was also highlighting, right? Anyone that had the computing justification to go into some of these portfolio computations that are optimization techniques would require subscribing to a quantum service. Now, how many in the financial services sector have a comparable appetite? It depends on the segment that you are in, right? So a retail bank may not be necessarily in the same level of appetite. It's not that their evolution would not make them suitable for consuming any particular capability in quantum. It's a matter of the type of problems that they may be dealing with, and then making the computing model more suitable for people that have much more demand in optimization techniques and things like that, right? So I would not put the full financial services industry in one bucket. I will divide them, and roughly, right? So ignoring clear outliers that you will find in each of these segments, you can order this more or less like data-driven work with all the vicissitudes that Paul mentioned in terms of legacies, with the advent of channels for capturing information that come from digital channels, that the digital channel transformation in the industry is common across all the segments, right, that deal with people particularly, right? People and other institutions, SMEs, right, small, medium enterprises. There are the thousands or dozens of thousands or hundreds of thousands customers of banks, for example. So for all what it has to do with digital channels, all the advent of mobile, security, all these things are at the front end of consumption. The adoption for those capabilities that have to do with dealing with mobility, dealing with security, dealing with data, and some form of personalization that data collection gives you at the early stages in customer experiences, for retail banking particularly. This is the mostly adopted of all the technologies that we are talking about. The next stage would be the back office activities in machine learning. It's very much tried in terms of center of competencies, particularly the large banks, the large financial market firms, the large, they have, the investment capability to try and create their own groups, work with third parties, even develop their own internal capabilities, have big center of competencies with a few hundred people in some banks, right? So this is, in some banks, you will find more data science people than in the best computer science department in some of the top universities. So I'm not comparing expertise in any way. I'm just alluding to volume, right? It's very
Right.
visible.
Right.
Right? It's very costly too. And then at the back end of the story, I mean, if you like to say the third stage of this, I would put blockchain first and then quantum. Once again, remember, I have averaged out the outliers and I'm not dividing by segment, right? Otherwise, it's not fair. But quantum is definitely catching up because of the conditions of usability and consumption by problem requirements. And blockchain is becoming extremely spoken, but it has a journey for adoption that is still facing even the wave of regulation coming in how they're going to accept or not these digital assets and the way they are being used in markets today, right? So that's a big question mark.
Thank you. Okay, so then I take from what you both said, I would wrap up with, I guess, 3 points that you mentioned. One is the segmentation of the financial services. It's not the same. We talk about retail banking. You're also talking about investment banking. So that would be one. The other is the having the skills and having like a center of excellence and how to team up with external knowledge, so with vendors, right? And then the other is understanding what is the benefit of the technology. So you were mentioning the quantum advantage for AI. What is it that I'm trying to get, and how do I scale it, right? So that it's not, we're not working in silos, and because that's one thing is to develop a technology, but the challenge is to maintain it, to maintain that benefit that it brings. So with this, I would like to thank you again very much for participating in this this talk and in this symposium. And if the listeners want to read more about your papers, they're available in the platform, so you can go into detail and read a bit more. They're number 24 and number 35. Okay, well, thank you very much. Thank
Thank
you
you very much. Yes.
Very nice seeing you, Paul.
Thank you.
Nice to meet you, Jorge.
Thank
Yeah,
you.
take care.
Have a nice day.
Thanks,
Thank
Elena.
you. Have a
Thank
good
you.
sleep, Elena.
Okay.
Have a good day. Thank you. Bye.
Thank you. Bye-bye now.
Bye-bye. Bye-bye. Bye, everyone.